Good day, everyone. I am April Vanessa C. Baldovino, your discussant for the Sieve of Eratosthenes. At the end of this lesson, the student should be able to use the sieve of Eratosthenes to find all prime numbers below a given integer n and determine a prime number using trial division. One of the Greek mathematicians whose work in number theory remains significant is Eratosthenes of Cyrene, who lived during 276 to 194 BC. The sieve of Eratosthenes is finding prime numbers by trial division. We have seen that if an integer a is greater than 1, is not divisible by prime p is less than or equal to the square root of a, then a is a prime. Eratosthenes used this fact as the basis of a clever technique for finding all primes below a given integer n. Now let's take a look at the proof of this theorem. If n is a composite integer, then n has a prime factor not exceeding the square root of n. Since n is composite, we can write n is equal to the product of a and b, where a and b are integers between 1 and n, and a is less than or equal to b. Suppose that a is greater than the square root of n, then a is less than or equal to b, but greater than square root of n. And as a result, the product of a and b is greater than the square root of n multiplied to the square root of n is equal to n. Therefore, a is less than or equal to the square root of n. Also, by the lemma of every integer greater than 1 has a prime divisor, a must have a prime divisor a sub 1, which is also a prime divisor of n. And thus, this divisor is less than a in square root of n. End of proof. Suppose we are asked to find all the primes not exceeding 100. Note that the square root of 100 is equal to 10, and the primes that are less than 10 are 2, 3, 5, and 7. This means that from the list of numbers 2 up to 100, all the composite numbers which are divisible by 2, 3, 5, and 7 will be removed. So that will be the even integers, the multiples of 3, the multiples of 5, and the numbers divisible by 7. And then we will be left with 25 prime numbers not exceeding 100. Is 149 a prime number? The nearest perfect square number to 149 is 144, and its root is 12. The prime number less than 12 are the primes that we are going to use to check if 149 is divisible of them. If not, we can conclude that 149 is a prime number. So those prime numbers are 2, 3, 5, 7, and 11. Remember that the sieve of Eratosthenes is finding prime numbers by trial division. So we're going to use 2 to divide 149. And we will see that 2 does not divide 149. 3 does not divide 149. 5 does not divide 149. 7 does not divide 149. And 11 does not divide 149. Therefore, we can conclude that 149 is a prime number. Determine if 509 is a prime or composite. The square root of 509 falls between 22 and 23. Hence, the primes that we need to try out are only 2, 3, 5, 7, 11, 13, 17, and 19 as possible divisors. We will see that 2, 3, 5, 7, 11, 13, 17, and 19 does not divide 509. Therefore, 509 is a prime number. Determine the canonical form of 2093. To determine which of the primes will be used, we need to get the square root of 2093. The square root of 2093 falls between 45 and 46. It is enough to examine the multiples of 2' up to 43'. We will see that 2093 is a product of a prime 7 and a number 299. Since we are not sure if 299 is a prime, we will repeat the process of trial division to 299. Hence, we will see that the square root of 299 falls between 17 and 18. We will use the primes less than 18 to divide 299. This will lead us that the 299 is a product of 13 and 23. Thus, the canonical form of 2093 is equal to 7 multiplied to 13 multiplied to 23. A prime number is a positive integer that is divisible only by itself and 1. To quantify the number of primes, let's define a function of pi of x to give the number of primes less than or equal to x. This function has nothing to do with the number pi. This is just the traditional name for the function. Pi of 6 equals 3 because the prime numbers less than or equal to 6 are 2, 3, and 5. Pi of 10 equals 4 because the only primes less than or equal to 10 are 2, 3, 5, and 7. The prime number theorem states that the ratio of pi of x to x over log x approaches 1 as x increases without bound. In symbols, the limit of the ratio of pi of x and x over log x as x approaches positive infinity is equal to 1, or the limit of the ratio of pi of x and x over ln x as x approaches positive infinity is 1. The prime number theorem says the prime of x is asymptotically equivalent to x over log x. From the previous example, the number of primes less than 100 is 25, and the ratio of x and ln x is equal to the ratio of 100, and ln 100 is approximately 21.715 or 21. From the formula, the limit of the ratio of pi of x and x over ln x as x approaches to positive infinity is 1. It will be 25 over 21, which is about 1.190. This implies that the pi of x is asymptotic to x over log x. Now on this episode, we're going to talk about the Fermat Factorization. Our objective is at the end of this lesson, the students should be able to use the Fermat Factorization to factor a given integer n. The Fermat Factorization was introduced by Pierre de Fermat, who was born on August 17, 1601 and lived until January 12, 1665. The Fermat factorization attempts to factor a number by representing it as the difference of two squares. This is the proof of Fermat's factorization. If n is equal to the product of a and b and n is odd, then a and b are odds. Let's say that a plus b and a minus b produced even numbers. Now, if a plus b over 2 is equal to s, and a minus b over 2 is equal to t, then we will have n is equal to the difference of the squares of a plus b over 2 and a minus b over 2. Then next, we're going to expand a plus b squared. It will give us a squared plus 2ab plus b squared over 2 times 2, that is 4, minus the quantity of the expansion of a minus b squared, which is a squared minus 2ab plus b squared over 4. Applying the rules of subtracting polynomials, by combining the like terms, we will have a squared minus a squared. It will give us 0. 2ab minus negative 2ab, it will give us 4ab. And b squared minus b squared, it will give us 0. And on the divisor, we will have 4. Now simplifying, we will have positive 4ab divided by 4. We will proceed to the result of the product of a and b. Thus, n is the difference of the squares of s and t. By substituting the integers s and t to the formula, n will be equal to s squared minus t squared, or by factoring, it will be the sum of s and t multiplied to the difference of s and t. End of proof. Let's have some illustrative example. Use the Fermat factorization to factor 1363. We begin by trying to find some number s, such that the square of s minus n is a perfect square. But how do we find the values that we will have to use? We will determine the starting point of the values of s by taking the square root of 1363. It will give us 36.918. We will get the round up of the number 36.91, so that will be 37. So we're going to use 37 as our s. Now, using the formula, we will find that t is equal to the square root of the square of s minus n. Then substituting the value of s, we will have the square root of 37 squared minus 1363. So we will have 37 multiplied to 37. We will have 1369 minus 1363. It will give us the square root of 6, which is not a perfect square. So we will then move on to the next number, 38, as s. So using s as 38, we will find that t will be equal to the square root of 38 multiplied to 38 minus 1063. So 38 multiplied to 38 minus 1363, it will give us the square root of 81. And 81 is a perfect square. Then we will get the square root of 81. We will have 9 as our t. Now, using the values of S as 38 and T as 9, we will have N is equal to the product of 38 plus 9 and 38 minus 9. Then 38 plus 9 is 47 and 38 minus 9 is 29. As you can see, 47 and 29 are both prime numbers. Therefore, using the Fermat factorization of to factor the 1363, the factors are 47 and 29. Let's have another example. Use the Fermat factorization to factor 2183. Again, we're going to find our first value of S, which is the square root of 2183, and it will give us 47. So our S will be 47, and then we're going to use that to find the value of T. So 47 times 47 minus 2183, it will give us the square root of 36, which is not what we're looking for. Then move on to the next number, to 47, that will be 48. Now we will have T as equal to the square root of 48 multiplied to 48 minus 2183. So that will be 48 multiplied to 48, 2304 minus 2183. That is 121, which is a perfect square. So since the square root of 121 is 11, it is going to be our T value. Now using the 48 as our S and T and 11, we will have N is equal to quantity 48 plus 11 multiplied to quantity 48 minus 11. Then we will have 59 multiplied to 37 as equal to N. As you can see again, 59 and 37 are both prime factors. Now we can now conclude that 2183 is equal to 59 multiplied to 37. Let's see if you learned something. Use the Fermat factorization to factor the following numbers. The answers on this is on the next slide. Thank you for listening.